Good morning and welcome back. Today we're going to do a brief video on the Ziegler Nichols closed loop tuning. Now it's interesting that it has an alternate name which is referred to as the ultimate gain method. This is a wonderful process tuning method that you can use in cases where you've possibly got a process that is integrating, and we would have dealt with that with an earlier video, or else a process where you are allowed to put the controller into manual and go and make the various adjustments that are required. Now, in the case of this loop tuning method, we're going to have a look for two specific values. We're going to get the KU value, and KU is going to be the gain value which gives you continuous oscillations. And then we also want to go and get the PU value. The PU value is going to be the ultimate frequency, the time of one complete cycle. Now, to make this nice and easy, I'm going to open up my simulator, which is there. And you can see that my simulator always must be set up so that it is going to be easy to use. Now, in this case, my simulator is measuring from 0 to 500 degrees Fahrenheit. It would not make a difference to my loop tuning, but I always like to work in percent. So I'm going to go and change the view and possibly just go and put that as 0 to 100%. The method is that you press your tuning button, you make sure that you are in manual. You go and start off with a low gain, maybe something such as 1. I'm going to have no integral. Now I'm working in minutes per repeat, so 100 is going to give me no integral, and my derivative is going to have a value of 0. Okay, what is the next step? We're going to try and get continuous oscillations. And one of three things is going to happen. The most common possibly is that your oscillations are going to either not appear or they're not going to be present. You might have a process variable that does something like that. Now, in that case, we can go and say that the system is overdamped. And if you have a system that is overdamped, what you want to do is you want to increase the gain setting. The second option is that you're going to have too many oscillations. When you give it a step change, the oscillations get bigger and bigger and bigger. That would be known as an underdamped system. And in the case of the underdamped system, what you want to do is you want to go and decrease your gain until you can get to the final goal. Now, the final goal is to have continuous oscillations. On a simulator, nice and easy. In the real world, it might vary ever so slightly, but you're going to get as close as you can. And at that point, you can tap yourself on the shoulder, because that is what we are looking for. And then you can go and get the value of KU, which was the gain that we would have been looking for. So let's go and do that first step quickly. I'm going to open up the simulator, and we'll start off with a small gain of 1, which is great. Put the controller into automatic, run the process, give it a step change, and have a look at, in our case, the red pen, the process variable. Now you can see that that is very much overdamped. So I need to go and increase the gain. Now, the nice safe way to do it, put the controller into manual, go to your tuning parameters. It's going to put in a value maybe of 4. You don't want to go too far. Put the controller back into automatic, give it a step change in either direction. All that I've done for my step change is just to change the set point. And as you can see, it is now starting to oscillate, but the oscillations are getting smaller and smaller. So again, I can go and increase the gain. Let's go and put in a gain maybe of 7 and see what that's going to do. I'm not going to put into auto manual all the time now, because this is a pretty safe process. So I'm going to give it a step change, and I'm looking at the red pen, which is my process variable. And as you can see, the oscillations are getting smaller and smaller and smaller. So maybe we can try a value of 10 and see what that does. Once it's oscillating, you don't need to give it a step change. Now, yeah, we can see that my oscillations are starting to get bigger. So 7 is too small, 10 is too big. Maybe we can go and try a value of 9. And remember, near enough is good enough. We don't have to work to the second or the third or the fourth decimal point. We're just trying to get a process that is continuously oscillating. And I think we've got exactly that. So I'm going to pause my screen. And the first thing that I can go and do is to go and write down the values that we have managed to achieve. So let's go to this page and we can go and say that KU was calculated, and that was a value of 9. Now you could get 9, 9.5, 8.9, whatever the case would be. You're going to look for a value that's going to work for you. And that's the first of the values that I need for my calculations. The second value that I need is the ultimate frequency, which is PU, and that is the duration of one complete cycle. Now, please, it's always a good idea to measure from the top to the top, or to measure from the bottom to the bottom. Don't try and measure from the middle, because sometimes the signal goes up and sometimes the signals go down. That is going to be my PU value. Getting back to my simulator, you can see that my time scale is in minutes. And if you look from the left to the right, 0 to 5 to 10, 15, 20, 25, 30. So every block is going to be about 5 minutes. Now maybe we can go and grab the signal from that point over there. It looks like 5, maybe 7.5 minutes. Would you agree with that? It's going to be a complete block and another half a block. So I can get a PU period of about 7.5 minutes. No rocket science, don't have to go and measure it. You just want to estimate near enough. So it looks like, if I go from the bottom again, 5 minutes, it probably looks like about 7 or 7.5 minutes. So I'm going to go and say that in our case, PU is going to be equal to 7.5 minutes. Great. Now that we've got that, we need to go and have a look at the Ziegler-Nichols methodology that has been put forward for us. Now, these are the Ziegler-Nichols formulas. These two gentlemen would have spent many, many years trying to study different loops between about 1938 and 1940, and they came up with a bunch of formula. What they said is that if you're only going to be dealing with a P control, for example with pressure or level, then you can go and just do the single calculation. If you're dealing with a faster process such as a flow control where you'd like to have PI control, well, then you need to calculate the gain and you need to calculate the integral. If you're dealing with a slow process such as pH or conductivity or temperature, then you want to go and use a PID, and then you'd have to go and calculate the gain, the integral, as well as the derivative separately. So your process would dictate what you are going to go and do. For those of you that are working with cascade control, PID would work on the primary or the master controller. We don't put derivative control on the secondary controller because derivative does not work very well on derivative. Now, I've gone and taken those formulas and put them into a spreadsheet. If you're in my class, you'd have to physically go and do the calculations, but I'm going to just make it a lot easier. So let's go to my spreadsheet. My spreadsheet is up in the middle of the screen, and all we have to go and do is put in the values that we've just gone and determined. The KU, the gain that we used for continuous oscillations, had a value of 9, and then we said that our ultimate frequency was probably about 7.5 minutes, and that's it. Put that in and have a look at how this does everything for us. If we're just doing a P control, then we got a gain value of 4.5. If you're doing a PI control, then Ziegler-Nichols will give us a gain of 4.05 and an interval time in minutes per repeat of 6.25. And if you are doing a full PID control, then you're going to get the gain value of 5.4, the integral of 3.75, and then a derivative that we are going to have of 0.938. Now that's what I'm going to use for my demonstration. So I'm going to go back to my simulator, and again, always a good idea to put the controller into manual, go to the tuning parameters and put in what you have calculated, which is 5.4 and 3.75 and 0.938, which is probably going to round off to 0.94. And that's it. Great. Okay. Run the process. Put the controller into automatic, and let's go and see what type of results we are going to achieve. Now, as you can see, spot on. And that is the nice thing of Ziegler Nichols. It is a very aggressive tuning regime which tries to get us maximum stability and maximum speed. When it works well, which is 19 times out of 20 or 95% of the time. If it doesn't work well, then you might just want to go and fine tune it. And in really serious applications where there's too many oscillations, I would often just go for half the gain and twice the integral if your integral is in minutes per repeat. And that should stabilize your process. One more test. And as you can see, we've got great stability that has come into play with our little process. That is it for this presentation. As always, there are going to be many videos that will come along. Please do look at them and share them widely. I actually have got a website which you can see at the bottom of this screen, and if you wish to know of the number of different workshops that I do present, well, that would be your first port of call. And please don't hesitate to give me a shout if I can assist you in any way whatsoever. It's been an absolute pleasure spending the last couple of minutes with you, and we will be doing a couple more videos very shortly. Thank you and goodbye.